Hello, everybody. Thank you for taking some time out of your day to join us. I'm very excited to welcome you to our online seminar on Lightspeed LNP formulation with Sunscreen. I'm joined today by Alex Kerr, one of our senior application scientists. How are you doing, Alex?
Very well, thanks, Ben.
Good. Excited to hear your presentation today. Before we get going, just for all of those of you joining live, there is a Q&A chat box in Zoom. So if you go down to the toolbar on your screen, you'll see the Q&A box. You can submit questions in there at any point during the talk, and we will be answering as many of those as we can at the end of Alex's slides. So please do submit those. We encourage you to choose to not to be anonymous so that we can follow up with you afterwards as well. But welcome any questions that you might have. So I'll come back to those at the end of the session. But without further ado, I'd like to hand over to Alex to get started.
Thanks a lot, Ben. And thank you everyone for coming along. Here at Unchained Labs, we are super excited to have a closer look at the first step of our sunny suite of products for LNP development. The Sunscreen, designed to accelerate and automate your formulation screening process. We'll be taking a look at why it's useful, how it works, and how we and our customers design screens and integrate it into our workflows. We know that with nanomedicine formulations, sometimes there's so many components, ratios, and processing parameters to explore that it can seem like you're lost in space, forever searching for that perfect formulation that's just one more experiment away. And sometimes that perfect formulation might just slip through your fingers. But we're here to show you how to accelerate your formulation development process to light speed with the fastest formulation kit in the galaxy. The BioNTech and Moderna COVID vaccines demonstrated the safety and efficacy of mRNA LNPs on a global scale. Their potential in vaccines and further types of drugs is now being realized across the biotech industry in treatments for cancer and even genetic therapy. These versatile particles enable the effective delivery of genetic material into cells within the body, where this material can be used to deliver instructions to your cellular machinery. And this all starts with the formulation. Lipid nanoparticles are typically composed of 4 lipidic components. Primarily, the ionizable lipid, probably the most significant component with the greatest molar percentage, and this binds the RNA and protects it in the core of the particle, and later helps release the nucleic acid into the cell. The structural lipids forms and stabilizes the outer shell of the particle. Cholesterol stabilizes the particle and is principally present in the core. And the pegylated lipids sit on the outside of the particle, which reduces the particle size and reduces the chance of aggregation. Finally, and increasingly, researchers are using a 5th component, which can range from charged lipids to grafted on antibodies, often to increase tissue specificity. And this blend has to be perfect. The different charges and structures of the lipids affect the properties of the particles. Here, you can see the difference that you may find when DSPC is replaced with DOPE, which are both structural lipids with slightly different shapes that affect the membrane curvature. This can affect how LNPs interact with the biomolecules in the body, in this case, leading to reduced binding of apolipoprotein E, and therefore decreased expression in the liver, which overexpresses low-density lipoprotein receptors. And that's not all. Once the particle gets to where it's going, the formulation affects 1, the cell uptake and endocytosis of the particle. 2, the endosomal escape, as the RNA has to escape into the intracellular space before being taken to the lysosome and broken down or recycled right out of the cell. Early clinical LNP formulations release as little as 2% of their cargo, so there's a lot to be gained from making this process more efficient. Finally, once the RNA has been released, it has to be translated, which is where the design of the nucleic acid really comes in. Base substitution, sequence engineering, and cap analogs all have a part to play in this. All of this, and we still haven't even mentioned immunogenicity or biodegradability. So, with dozens or even hundreds of different lipid types, RNA modifications, and process parameters, there are literally millions of potential experiments. So, there needs to be a way to screen a lot of formulations with a high degree of accuracy and reproducibility, which is where the Sunscreen comes in. With 96 well plates for your reagents and collected samples and full automation once your experiments are running, you can really crank out experiments like never before. The system uses driving fluids to move your pressure sample around the system and mix them together, meaning you can use as little as 100 microliters per input, which keeps your reagent costs down. And when you have the capability to run hundreds of experiments a week, using less reagent makes a big difference to your costs. With reusable microfluidics and a directly translatable process right through to continuous manufacturing, Sunscreen is really one of a kind when it comes to nanoparticle formulation screening. And when you have the ability to screen hundreds of experiments, you really need to be confident in the consistency of the process you're using, so you don't end up having to repeat them all, and you know that results between different experiments are fully comparable. With Sunscreen, you can produce highly consistent data from repeat experiments, even if you just ran a not-so-good formulation, because the system self-washes between every experiment to ensure excellent experimental fidelity, even for very differently behaving formulations. Here you can see an example of where we've run a 96 well plate screen with 6 experiments that were intentionally run to cause massive aggregation by excluding the PEG component of the formulation. You can see that the formulations that were run directly after these catastrophically aggregated formulations were still of top quality with no statistical difference to any of the other experiments. And those 90 experiments showed an astounding CV of less than 1% for the Z average over 90 repeats. So you really can be sure that when you run a plate of formulations on Sunscreen, you can be confident in that data you've produced. And the range of applications is huge. We have customers screening, for example, different nucleic acid cargoes with the same lipid formulation, e.g. different caps or base substitutions, to take on to cell testing, knowing that all the particles will be of great quality and directly comparable to others in the screen run in the same conditions. Probably the most common application of Sunscreen is in screening lipid formulations, and most particularly ionizable lipid libraries. Using Sunscreen allows them to get that invaluable comparative data for the different components, whilst being sure that each experiment is a realistic and reproducible sample that can be rerun easily and scaled up with a minimum of effort. But what does running a screen look like? We're going to quickly take you through the process of running a large-scale screen on the Sunscreen, where we were looking at adjusting the levels and identities of different lipid components across 32 different formulations and 96 experiments, looking at the effect on the biophysical characteristics of the LNPs. And the first step of that is selecting your Sunny. The Sunnies are microfluidic chips where the mixing event takes place. Here you can see us mixing 2 dyes representing your lipid and aqueous phases. The Sunnies are ultra-smooth glass with great chemical stability and a surface roughness as low as 5 nanometers, and this is compared to between 1 and 3 microns for injection molded chips. This, combined with the automated washing between experiments, allows for reuse after reuse. But which Sunny should you choose? Unchained offers a range of Sunnies, and which one is best for you will depend on your exact applications that you have in mind. This is a list of most of our currently available standard Sunnies and the types of mixing they are used for, but we are always on hand to give our input on the topic too. As an example, and to look at the 2 extremes, here we have the Trident 490, which is designed for ease of use with a built-in dilution channel for high throughput, low back pressure screening. This uses gentle laminar mixing and provides exquisite control of the particle size. For our screen, we're going to be using the Trident Sunny for this reason. On the other hand, on the right here, we have the micromixer. This is sort of our equivalent of the staggered herringbone mixer with complex internal geometry to create serious chaotic flow and lateral mixing for very rapid mixing, which therefore produces really small particles, even at very low flow rates. And remember, every formulation behaves differently. Here you can see the difference in size response to flow rate of a formulation based on either SM102 or DOTAT. And you can see the different response they have to increasing flow rates. So running an initial screen on your selected Sunny with a representative formulation can ensure you're getting roughly where you want to be with a given lipid mix. We're using a DOTAP formulation and decided based on this data that we would use flow rates of 9 ml per minute. So we'd be targeting sizes around 90 nanometers. And finally, you can tailor your configuration. This can be as simple as adding dilution or not adding dilution, but can also be more complex. For example, typically we run just our aqueous phase and lipidic phase as the initial mixing step. But we have other examples. We had one customer who was concerned about the long-term stability of their cargo in acidic buffer. And so in conversation with them and using just the standard setup of the equipment, we were able to add an acidic buffer, the cargo in a neutral buffer, and the lipids all at the same time. We used our standard micromixer chip to ensure that all the phases rapidly mixed, which helped to preserve good particle properties and high encapsulation efficiencies that you learn to expect from Sunscreen, whilst preserving that precious cargo. Once you've decided on a Sunny and a set of conditions, you can now design your experiment. The Sunny Suite software allows you to design experiments using an import spreadsheet, meaning you can do it anywhere, in the lab, in the office, or even at home. It even validates your experiments, so you can ensure that all the conditions are within spec. Even if you run an experiment that's technically out of spec, the software will see that when you upload the spreadsheet and will just skip over that experiment so it won't mess up your whole formulation screen. You can see here we've set a sample size of 800 microliters with a 10% head and tail cut to waste. These figures are fully customizable to your testing needs, so you can get full collection of sample by collecting the full sample with no sending material to waste, or you can just get that very central heart cut of the experiment to best represent what you might get in fully continuous production. The software even tells you what the runtime and the driving fluid usage will be at the bottom here. This means that you can help plan your large experiments easily. Finally, it tells you how to lay out your well plates. So you can see here, it's named the formulation that's going into each cell, and it's also told you what amount to put into each well, just in case you're varying that. This is just input 2 well plate, which in this case is our lipids, but it also gives you this both for input 1, your mRNA solutions, and for your output plate. Once the experimental set is designed and the plate is loaded, the spreadsheet can be uploaded into the software, you press start, and you can walk away. Now you can get on with prepping for particle processing, planning, and preparing the next screen, or analyzing yesterday's dialyzed particles. Talking of analysis, a great unchained synergy is using the Stunner, which is a 96 well plate format, DLS and UV vis system, which really helps to boost your analytical throughput. This uses just 2 microliters per sample to get the particle size, PDI, and uniquely total RNA concentration from your LNPs, really cutting down on that downstream analytical workflow. And here are the results of the screen. 32 formulations in triplicate, all with PDIs less than 0.2 and really good agreement between triplicates. You can see what you'd expect as PEG concentration increases. The particle size drops in each case. But what else did this one experiment uncover? So we compared the lipids DOTAP and DDAB across these formulations, which are 2 common cationic lipids, here standing in for the more complex ionizable lipids often used in clinical formulations. In most of the formulations group, DOTAP produced smaller particles than DDAB, though DDAB had the edge in lower PDIs, at least when pegged with DMG PEG 2000. We also compared 2 structural lipids, DSPC and DOPE, which we mentioned before. And it was interesting to see that they had no significant effect on particle size. However, we did see that DOPE gave slightly consistently larger PDIs. So if you're really looking for tight distribution of particles, DSPC might just give you that edge. As expected, the PEG molar percentage inversely correlated to particle size, but this also shows diminishing returns, with this effect greatly leveling out as you continue to increase the concentration of the PEG lipid. Interestingly, DSPE PEG 2000 shows a greater effect on particle size, with a more extreme gradient in both larger large particles and smaller small particles. The effect overall on the PDI was really minimal, but encapsulation efficiency did show a minor difference. And because of the amount of data we have and how granularly we can separate these experiments, we could track this down specifically to a combination of DDAB and DSPE PEG 2000 combinations. Now, you can see the encapsulation efficiency for these experiments was still pretty high, but you would think, taking this forward into the next round of experiments, that might be a combination you want to avoid. So Sunscreen allows you to uncover essential information like this in one day, every day, at scale and with precision and confidence, so you can direct your formulations to the perfect sunny spot every time. We stopped here in our assay, but what you do next is up to you. Of course, a common one is cell transfection. For example, a luciferase assay. You can see the results of a simple one on the left there that we run in-house. Some of our customers fully dialyze the particles after running a screen, and other ones even just rely on a quick dilution to reduce ethanol content before running a cell screen to really make a rapid process. After or alongside that, many of our customers have started in vivo screening with particles produced on the Sunscreen, as this data from a customer shows. Once you found that rock-solid formulation on Sunscreen, Sunshine helps you tune in your LNP size and design the perfect process to scale them up. Scout ideal flow rates, mixing geometries, buffers, and dilution factors to keep them stable. Once you've got everything just right, Sunshine can switch from protocol mode into continuous mode, making up to tens of liters per day and giving you a process development and scale-up platform. Because our systems use the same pumping technology, sunnies, and tubing types from screening all the way through to continuous manufacture, you really can get the same results from both systems in either operation mode without having to change the process parameters, which really helps reduce that painful and expensive process validation when you switch up to the next step of development. So, let us accelerate your LNP development pathway to Lightspeed. Hopefully, you've got a good idea of how simple working with the Sunscreen can be and what it could do for your workflows. Thanks for your attention, and I'd be happy to answer any questions you might have.
Brilliant. Thank you so much, Alex. That was excellent. We've got some questions coming in already, but as we start to answer a few of those, please feel free to keep them coming. We're happy to answer as many as we can with the time we have. So I'm going to start off with one that came through early on, asking whether or not we can screen technologies other than LNPs, Alex.
For sure, yeah. So we're still working on that data to show you. But absolutely, we have customers working in anything as various as liposomes through to polymer nanoparticles and other fully aqueous polyplexing systems. So it's really adaptable to different screening techniques. For each experiment, you can change things like your flow rate ratios and total flow rate. So even if there's a slightly different mixing modality to what you'd expect to LNPs, we can still be confident that you can take whatever technology it is that you're working on through on Sunscreen.
Great, thank you. And another question asking about how you make sure that those experiments don't contaminate one another.
Yeah, of course. That's always going to be a concern when you're using the same sunny over and over again. I did talk about how smooth that microfluidic mixing device is. However, because the device uses driving fluid to push the packets of sample through the system, we can double that fluid up as cleaning fluid. So in between each experiment, a certain amount of cleaning fluid or driving fluid is run through that mixing device as well. And we have done extensive testing in-house with various compounds such as RNAs or fluorescein, so we can easily detect contamination, to run various experiments through the device to detect what volumes are necessary to get really good cleaning. And we have set that at a certain volume for the experiments that we ran, but we also still do give the additional option to run more extensive wash cycles between experiments if you do think it will be necessary.
Great, so that's user tunable as well.
Absolutely.
Awesome. And next question is around how long it took you to prep a full 96 well plate with all those different lipid formulations.
Yeah, that's a really good question. And really, it depends on what you're screening. We can recommend a few ways to make that simpler. For example, if you're just screening ionizable lipids, we would recommend, rather than setting, say, a certain milligram per mil of lipid, set a concentration, like a millimolar of lipids. So that means that for each experiment, you can use the same supporting lipids and just adjust the exact concentration of ionizable lipid that you're adding, which helps really cut down on making really small adjustments based on that ionizable lipid's molecular weight. Additionally, what this really helps you do is means that input 1, so let's say the RNA, is going to be matched to that ionizable lipid concentration. And so that RNA concentration can be the same in every well if the concentration of the ionizable lipid is the same in every well that it's reacting with. So that's how we'd sort of recommend laying that out. And depending on how complex your formulation is, that could take as little as half an hour. Now, I have run a 96 well plate screen in the past where I was working with different concentrations that each required different amounts of the various materials, and that did take a bit longer. And that's all about your planning, which the spreadsheet that the software, the import spreadsheet develops really helps with. But even then, I would say it wouldn't take me more than an hour to fill 2 full plates. And that's really a worst case scenario. If you've got a really well-designed screen, I would hope and assume that you could get that done within sort of 15 minutes.
Perfect. And then another question here asking, what are the consumables on the device?
Yeah, sure. So we've talked about the Sunny and how it's pretty much indefinitely reusable. We do suggest that you might want to swap that out every 3 months or so, just for good measure. And then there are also the syringes in the tubing. Again, this depends on wear and usage and your personal judgment when you're running the device, but we'd suggest a replacement time of between 3 and 6 months for those. But compared to anything that's single use or limited use, like 5 experiments, it's by far and away much more convenient and much easier to factor into your quarterly budgets.
Yeah, so that per runtime experiment gets pushed way down.
Yeah, absolutely.
Awesome.
Yeah, so the 3 months, sorry, just to clarify, 3 months could easily be thousands of individual experiments.
Yeah. Great. And so the next question I have here is how we suggest dialysis, and another person's also asked what downstream processing methods we use. So perhaps there's a joint answer there.
Yeah, so we're often asked about this. So Unchained Labs does provide a couple of downstream processing solutions for buffer exchange in the shape of the Unagi and Big Tuna. So watch out for more data on those and LNPs in the coming year. Other than that, it's really up to you. So like I mentioned earlier, some people are just running sort of 10 times dilutions and then putting these particles on cells, because that's enough to get the ethanol concentration down to where it's not significantly hazardous for a cell. We have other people who use various dialysis cassettes or centrifugal cassettes to buffer exchange, and this really depends on your personal preference. Again, some people use a cassette with a really high molecular weight cutoff and do very short dialysis. Some do a full 24 hours, and we can help you develop a workflow if you're interested in seeing what that might look like. But really, it's up to you and what formulation and dialysis you prefer to use.
Thank you. And another person has asked about the average run time for the Sunscreen and whether particles are stable after a full run.
Yeah, sure. So for a full 96 well plate run at pretty standard conditions, you're looking at 5 to 5.5 hours, give or take. We've done some screening with LNP formulations with mRNA and done cell assays afterwards and seen pretty equivalent transfection before and after the well plate screen. So first sample, last sample. Obviously, different people are working with really different materials, and it could be that either your lipid formulation or your cargo has really hard limits on its stability over time. So there's a couple of things that you can do to think about improving that performance, and that could be using additional dilution to help reduce that ethanol content so they're more stable on the plate for longer. Or, and I think this is really important to highlight, perhaps I should have put it in the presentation itself, you can run as few or as many experiments as you want. There's nothing driving you to produce 96 experiments. It can be tempting to do that, but really you get just as much benefit from running a half plate or 2 rows of formulation. In fact, sometimes I like to run 2 rows of formulation at once. So that's 24 experiments on a 96 well plate, because then whilst that's running, I can prepare the next 24 experiments. And then whilst those next 24 experiments, I can take those first experiments. And with the stunner, I've got plenty of time to analyze them and plenty of time to start preparing the downstream dialysis protocols that I'll be running. And those will all be done by the time the next set of experiments are ready, and so on and so on. So, depending on what you're using, you may or may not have formulations that are stable for the full 6 hours, but what you can do is make your workflow or make Sunscreen work for your workflow, depending on what those lines are.
Great. So yeah, so you can optimize for how long it takes for your next step and things like that as well. So make sure that you're producing samples that take up an equivalent amount of time, and so you can keep a nice continuous process. Cool.
Exactly.
So there are a couple of questions about stunner. So question here saying stunner samples have to be diluted.
So one of the really nice things about stunner is that LNP samples don't have to be diluted because stunner is a special microfluidic plate. It actually has 2 little viewing windows in the plate that the sample goes through, and one of those is wider than the other. So the device will look at the turbidity of the samples, and it'll actually decide whether to use the full path length cuvette or the thinner high turbidity cuvette. So you can get really accurate readings even for quite concentrated samples, which is really nice.
Awesome. And that sort of touches on the other question that came through as well, which is how does stunner use such small sample volumes? Which really relates to that microfluidic.
Yeah, sure. No, that's a really good question. So you don't just put your plate straight on the stunner and let it sit there. You take just 2 microliters of sample out of your LNPs that you formed, and then the stunner uses a microfluidic plate. So you add just that 2 microliters to the entrance of a small well, which then wicks into a channel. And then the stunner itself has a pump in it that it will pump the sample through to the cuvettes for reading.
Great. Another question has come through here on the sunnies themselves, asking a little about the geometric differences between the different mixer types, and can the flow be changed by changing total flow rate to affect the Reynolds number? So and whether we have any data on that.
Sure. So we don't have any data directly on the Reynolds number, well, we do on the Reynolds number, but not on the turbulent flow. We get our data essentially from the results that we get from running the chips. So you can see a characteristic rapid drop in particle size when some of the chips hit a turbulent flow regime. For example, the 100 micron junction chip, or the 100 XT Sunny, you see at 2 mil a minute produces quite large particles. Then at 4 mils a minute, there's a massive rapid drop, which you can see particle sizes dropping by over 50% when that flow has clearly moved into the turbulent regime. The designs of chip are designed to induce these different types of flow. And of course, Reynolds number isn't the whole story necessarily when you're using complex geometries or smashing flows into each other, such as with a T mixer.
Great. And on the sunnies as well, is it possible to have inline dilution on each of the sunnies?
Yeah, that's a really good question. So yes, is the answer to that. I did mention that Trident has the built-in dilution, which makes it really simple to use. But with the other chips that might not have built-in dilution, you can run a series of 2 chips in series. So you have that first mixing step on one chip that then goes to a second mixing chip where the dilution process takes place. And so you can tailor both the initial mixing and the dilution if you so desire. So you can use various different chips with dilution.
Brilliant, thank you. All right, so I think that's all the questions we have time for in this session. Thank you so much, Alex, for taking the time to answer those. If anyone had any questions we didn't have time to get around to, we'll have to reach out after the session. And for anybody watching the recording of this, please do reach out to us if you have any additional questions as well. Thanks everyone for your time today, and we look forward to seeing you in our next seminar. Thanks.
Thanks a lot.